Welcome to the Teja Statistics. Today we are learning the recurrence relation of Poisson distribution. The PMF of the Poisson distribution is given by P of x equals to e to the power of minus lambda, lambda to the power of x divided by x factorial. The moments are given by mu r equals to expected value of x minus x bar whole to the power of r. For the Poisson distribution, we have e of x value as lambda, so just substitute over here, that is e of x value x minus lambda whole to the power of r into p of x, that implies x minus lambda whole to the power of r. What is the p of x of the Poisson distribution? E to the power of minus lambda, lambda to the power of x divided by x factorial. So if you common some value, that is 1 divided by x factorial, this will be the value of summation x minus lambda whole to the power of r e to the power of minus lambda and lambda to the power of x. Here the lambda is the parameter, then the differentiate with respect to the value of lambda, then mu r d by d lambda of mu r. So here you have to apply the UVW formula if you know, or else you can use UV formula also. Okay, so 1 by x factorial is common, so x minus lambda whole to the power of r e to the power of minus lambda is putting as a constant. So just u we are supposing, just v we are supposing. So x into lambda to the power of x minus 1, if you differentiate with respect to the lambda, plus x minus lambda whole to the power of r and lambda to the power of x is a constant, then you will get the value as minus 1 like this. And again you have the uv formula, that is e to the power of minus lambda, lambda to the power of x and r into x minus lambda whole to the power of r minus 1 and minus 1 you are going to get. So from that you are taking one common values, x minus lambda whole to the power of r divided by summation x factorial. So e to the power of minus lambda x of x, lambda to the power of x minus 1, and this will be the minus lambda to the power of x e to the power of minus lambda r into e to the power of minus lambda, lambda to the power of x divided by x minus lambda value. So here if you common the overall function x minus lambda whole to the power of r e to the power of minus lambda, lambda to the power of x divided by x factorial, this is the PMF of the Poisson distribution and the extra term. So if you do the LCM, then you will get the value like this, x minus lambda divided by lambda and r divided by x minus lambda. So if you multiply the total function over here, then you will get uh, d by d lambda of mu r equals to mu r plus 1. This is in the form of the, when bases are equal, powers should be added. So x minus lambda whole to the power of r e to the power of minus lambda, lambda to the power of x divided by x factorial is the p of x and extra term is lambda. So mu r plus 1, this is the formula for mu r plus 1, and this is the value of mu r minus 1. So extra term is mu r minus 1. So mu r plus 1 you have to derive for the recurrence relation. So here you are getting that value only. So just mu r plus 1 divided by lambda minus r into mu r minus 1. So from that you are aiming mu r plus 1 divided by lambda. So this will bring this side. So d by d lambda of mu r plus r into mu r minus 1. So if you multiply with lambda, then you will get the mu r plus 1. So this is called the recurrence relation for which distribution? Poisson distribution. Very very important questions we are discussing. Next, the CGF of the Poisson distribution is also they are regularly asking in our examination. So logarithm value of mx of t of the Poisson distribution we are substituting. Then logarithm value of lambda of e to the power of t minus 1. If you substitute, then you will get the value of kx of t lambda into e to the power of t minus 1. So the mean value of from the CGF you are trying to find out. So just see d by dt, okay, of kx of t at t equals to 0. This is called k1 also. Okay, so k1 is nothing but mean. So lambda e to the power of t minus 1 is common. So here lambda into e to the power of t, you are going to get, if you substitute t equals to 0, then the mean value as lambda. Next, mu2 is nothing but k2. Okay, d square by dt square of kx of t at t equals to 0, d by dt of lambda into e to the power of t. So lambda is a constant e to the power of t. If you put like that, then you are going to get the mu2 value as lambda. Next, k3 also you are going to get the as lambda. K4 also you are going to get the lambda. So what is mu4? K4 plus 3 into k2 square. So lambda plus 3 lambda square. So from that, what is the beta 1 value? That is skewness. That is skewness. So what is skewness? Mu3 square divided by mu2 cube. So lambda 3 is mu3 is lambda to the power of 2. Lambda mu2 is also be the lambda power 3, 1 divided by lambda. It is a positively skewed data. Next, Curtis is beta 2 equals to mu4 divided by mu2 square. So this will be 1 divided by lambda plus 3. So plus 3 if you got, then it is a uh, leptokutric curve. Okay, this is how you have to derive for CGF of the Poisson distribution with respect to their fourth order movements and also beta 1 and beta 2 respectively. And you have to comment on the given data also. Okay, this is what they are asking in our examination, the recurrence relation and CGF of the Poisson distribution. Okay, next we will continue with some another concepts in the Poisson distribution. The next property of this Poisson distribution is additive property. Additive property of the Poisson distribution. The statement, the sum of two independent Poisson random variables is again a Poisson distribution, or else if x follows the Poisson of lambda 1 and a y follows Poisson of lambda 2, then x plus y follows lambda 1 Poisson of lambda 1 plus lambda 2. So the PMF of the Poisson distribution is given by P of x e to the power of minus lambda, lambda to the power of x divided by x factorial. The MGF of the Poisson distribution is given by, so x follows, so the the MGF of the Poisson distribution is given by mx of t is equals to e to the power of lambda e to the power of t minus 1. If x follows Poisson of lambda 1, then its MGF is given by e to the power of lambda 1 e to the power of t minus 1. Next, y follows, then its MGF is given by my of t is equals to e to the power of lambda 2 e to the power of t minus 1. Next, now we already know the property. So what is that property? So the mx plus y of t, that is equals to mx of t into my of t. So where e to the power of mx of t value is e to the power of lambda 1 e to the power of t minus 1, my of t value e to the power of lambda 2 e to the power of t minus 1. When if you common, then bases are equal, power should be added. This is in the form of the uh, MGF of Poisson distribution. Therefore, x plus y follows p of lambda 1 plus lambda 2. The sum of two independent Poisson random variables is again a Poisson random variable. Okay, next. Show that the binomial distribution tends to the Poisson distribution as n tends to infinity and np equals to lambda. The The PMF of Poisson distribution is given by P of x equals to, sorry, this is the binomial distribution. So first of all we are writing the Poisson distribution is the target. So here binomial distribution we are writing ncx p to the power of x q to the power of n minus x. From that they given np equals to lambda and p equals to lambda divided by n, q equals to 1 minus lambda divided by n. Now consider p of x equals to ncx p to the power of x q to the power of n minus x. So this is a expansion of this. So n of n minus 1, n minus 2 and so on, n minus of x minus 1. So p to the power of x into q to the power of n minus x. So if you common that n value from here, so n of 1 minus 1 divided by n, 1 minus 2 divided by n, so on, n of 1 minus x divided by n plus 1 divided by n. If you common, and x divided by x factorial will remain same, and p to the power of x and q to the power of n minus x. Just how many values of n are there? There are x number of values. So n to the power of x, we are writing n to the power of x we are writing, and 1 minus 1 divided by n, 1 minus 2 divided by n and so on, 1 minus x divided by n plus 1 divided by n, and p to the power of x and q to the power of n minus x will remains the same, and x factor also will be the same. So next we are substituting n power x is there, p to the power of x is also there. We are putting np whole to the power of x divided by x factorial. So remaining things remain same. Next, what is the value they given? Np is equals to lambda to the power of x divided by x factorial. So this is very little and simple terminology, and we are taken from the given data. Q equals to 1 minus 1 divided by n. So and np equals to lambda, we are substituting over here. So 1 minus lambda divided by n whole to the power of x. Here it is a power, here it is n power, and here it is x power. Okay, now apply limits on both sides, and as n tends to infinity, 1 by n tends to 0. So this total values will be begin. This total value will be begin. So and 1 by n tends to zeros. Okay, and limit as n tends to infinity only will be there. So this is the value of e to the power of minus lambda. This is the value as 1 only. So lambda power x divided by x factorial. This is the PMF of e to the power of minus lambda to the power of x divided by x factorial, which is in the Poisson distribution. Okay, this is very important relation for the Poisson conversion from the binomial distribution. Thank you.